Welcome. I would like to tell you about Darcy's law. This is a cross-section through a flat landscape. Here we have the land surface. We see sand grains here. Here we have the water table. And here we have groundwater. And installed into the subsoil are two piezometers. In Dutch we call that stijghoogtebuizen. And we have a piezometer here with a screen at the bottom and a piezometer here with a screen at the bottom. And water can only flow into these piezometer tubes through the screen, through the bottom. So we can see that the water is rising to a higher level here in this piezometer than it's rising in respect to a reference level in this piezometer. Water is flowing from left to right, and we can see the water level is differing 1 meter in height, and that 1 meter in height is established over 1 kilometer distance. The question is, can we estimate the velocity of the groundwater flow? Yes, we can, and for this we can make good use of Darcy's law. But before we do that, let's do a little quiz, a multiple choice question. By law of nature, water flows from high to low elevation. Is that the right answer, or is the right answer by law of nature water flows from high to low energy? Or does it by law of nature flow from high to low water pressure? Or are all of the above options true? Think about this. There's only one right answer. What is the right answer? What do you think now? And what do you think after you've seen this video lecture? Let's move to this model between two glass plates. This is a model that we use during the open days of the Bachelor Institute of Earth Sciences here at Utrecht University. We have a model between two glass plates, and this is the glass plate in front, and there's 5 centimeters further down. There is another glass plate about 5 centimeters apart. This is about 75 centimeters high, and this is 1.5 meters wide. And in actual fact, this is a replica of the subsoil being 80 meters high and 13 kilometers wide. So there is a pronounced exaggeration of the vertical in respect to the horizontal. We see gravel here, and we have sand there. And in the real world, this is sand, and this will be clay. We have a higher part of the landscape here, and here we have the flatter, polder part of the landscape. It's raining. Water is moving out of the model in this ditch, and water is moving out of the model in this river. The water table is approximately like this. Of course, it coincides with the surface water level here, and also here we have the water table like this, and it coincides with your surface water level here. From the back of the panel, a coloring dye is injected into the system, and this enables us to follow the pathway that the groundwater flow takes. And we see that groundwater flow from here flows in this manner through these two clay lenses and then flows into the river. We call this a sub-regional or a regional flow line, and here we have a local flow line, and we can also see the movement of the water. So what do we see? We see that water is flowing along curved pathways, and we see that water can easily flow upward from a low to a high elevation. There's no problem in that. And also in reality, rivers are fed from below. And here we see, if we look here, we have a larger column of water than if we look there, we have a shorter column of water. So water is flowing from a lower water pressure to a higher water pressure. It's flowing from a high to a low elevation, but from a lower to a higher water pressure. And here water is flowing from a higher to a lower water pressure, but from a lower to a higher elevation. So water can flow from high to low elevation, from low to high elevation, or from high to low water pressure and from low to high water pressure. There's no problem there. So what then makes water flow? Well, of course, this is a picture showing you the polder landscape again. Here we have a higher water level to which the water from the polder is pumped. And if we would not do that, water would start to rise, thus flow from a low to a high elevation. So we already knew that water can flow from a low to a high elevation. In actual fact, you already knew that water does not necessarily, by law of nature, need to flow from high to low water pressure, because if you look at the water in this cylinder, the higher water pressure is here at the bottom and the lower water pressure is here at the interface of the water with the air above. The water is at a standstill in this model. It does not, by law of nature, flow from a higher water pressure to a lower water pressure. So now we already know that two of the options in the multiple choice question, water flows from high to low elevation and water flows from high to low water pressure, are not true. Water flows from high to low energy, and we can very simply measure that energy using a piezometer, een stijghoogtebuis. So your hydraulic head, if we take this as a reference level, is simply this height, which I'm indicating now. Your total energy here, your hydraulic head, is this height. So we have a higher hydraulic energy, a higher total energy here than there, meaning that water is flowing downward. Here we have the river. Of course, this was the upper part of your landscape, with here your water table. Water table coincides with your surface water level here. And if we install two piezometer tubes here also, of course you must take care that there's no leakage from the river water. We can estimate, or we can actually determine the hydraulic head here simply as the height to which the water rises again in this tube in respect to this reference level. So this is the hydraulic head at this location, and this is your hydraulic head at that location. So my hydraulic head here, deeper down in the subsurface, is higher than my hydraulic head here, higher up in the subsurface, meaning that water is flowing upward. If we were to install more piezometers, we could establish this figure of streamlines, where water is flowing. Here it's recharging, and here it's discharging into the river. And in actual fact, these broken lines are lines of equal energy, of equal hydraulic head. So this is a higher hydraulic head, this is a lower hydraulic head, and this is an even lower hydraulic head than here. Water is always flowing from a higher to a lower energy, or from a high to a low hydraulic head. If we look at Bernoulli's law, Bernoulli's law states that if there is no loss of mechanical energy due to friction, and also if we take water as incompressible, then for steady groundwater flow, Bernoulli's law states that the sum of certain energy terms is constant. In actual fact, there are three interchangeable energy terms. One is kinetic energy, which has to do with the velocity of the groundwater. I can already tell you that the velocity of groundwater is very low. Groundwater flows very, very slowly. So we can forget about that term in Bernoulli's law. So you don't see it here. Instead, you only see here potential energy, and you see here pressure energy. Of course, M is the mass of the water in kilogram. G is the acceleration due to gravity, which is approximately 10 meters per square second. And Z is the height or the altitude above reference level. kilograms times meter per squared second times meters gives you joule as an energy term here. Here we have the pressure. This is your pressure energy. P is pressure in Newton per square meter, and V is your volume of your water in cubic meter. So Newton per square meters times cubic meters gives you Newton meters, which is also joule. So this is constant, as I just told you, and we can simplify the equation. We can divide all terms to the left and the right of the equal sign by the volume of the water. And so you could also say we're looking at a certain volume in the subsoil. Then mass, of course, becomes density, so kilogram becomes kilogram per cubic meter. These, of course, stay the same. And if we divide by volume, your PV terms, of course, becomes P. And this is also constant. In actual fact, this constant now divided by V, by the volume. We can simplify it even further. What we can do is we can divide by the density, because fresh groundwater has a constant density of 1000 kilogram per cubic meters, and we can divide by the acceleration due to gravity, because that's at a certain location is also a constant. And if we do that, if we divide rho g z by rho g, of course we get c, and if we divide p by rho g z, this is what we get. And also these terms added together are constant. And of course what we see now, this term is in joule, also this one of course, but now we find here the terms in meters. So we have come from energy terms in joule to energy terms expressed as a length unit. And what's the connection with the piezometer tube? Well, let's tell you first about this. Also, the connection will become clear. This constant, we call it the hydraulic head, stijghoogte. The Z we call elevation head, plaatshoogte in Dutch, and P divided by rho G, we call it pressure head or drukhoogte in Dutch. So if we have a piezometer tube, and I already explained water can only flow in through the bottom of the tube, through the screen, then Z is simply the altitude above your reference level. P divided by rho G is simply the water pressure here at this location. And if we add Z plus P divided by rho G together, we get H, the hydraulic head. So hydraulic head equals elevation head plus pressure head. And the Dutch words hydraulic head, stijghoogte, elevation head, plaatshoogte, and pressure head, drukhoogte. And again, a piezometer tube, in Dutch we call that a stijghoogtebuis. So if you have horizontal groundwater flow, this is a ditch, this is a cross section through the landscape of course. We have installed two piezometer tubes with their screens at the same altitude above this reference level. We find that the water flows to a higher level in this tube in comparison to this tube. So here we have a higher hydraulic head, a higher total energy than there, meaning that water is flowing in the direction of the lower hydraulic head H2, and that in actual fact, if I come back to the earlier multiple choice question, the right answer must be that water flow is from a high to a low energy, from a high to a low hydraulic head. This of course is horizontal groundwater flow, but if we were to install two piezometers close together in the subsoil, one with its screen at deeper down in the subsoil and one with the screen not so deep down in the subsoil, then we could simply establish water is always flowing from a high to a lower hydraulic head, the direction of the water flow. Well, here we find at a higher location in the subsoil a higher hydraulic head H1 than deeper down. Here we have a hydraulic head H2, meaning that water is flowing downward seepage, and with a a kind of old-fashioned Dutch term. We call that wegzijging. Here we have the opposite. Here we have water which is flowing upward. And why is that? It's simply because we're measuring a higher hydraulic head here, a higher total energy here than we are measuring here. And in Dutch we call this, in English we call this upward seepage, and in Dutch we call this kwel. Let's do a little mind experiment to show you the difference between velocity and volume flux density. It's raining, and let's imagine that it's raining on a soil which is 100% dry. So we have 5 millimeters of rainfall in an hour, and you can think of that 5 millimeters of rainfall as a layer on top of your land surface, which is infiltrating into the pore space of your subsoil. The question is, how deep will the water infiltrate into this 100% dry soil? Well, let me ask you, will it be 5 millimeters? Or will it be less? Or will it be more than 5 millimeters? Of course, it has to be more than 5 millimeters because your subsoil is made up of pores. And in between these pores, these minute holes in the soil, we have solid substances. We call that the matrix. So let's imagine that water infiltrates to a depth of 15 millimeters. You could first of all ask yourself, how much volume of pores do I have in the subsurface as compared to the total subsurface? Well, that must be 1/3. If I have 5 millimeters of rainfall and this infiltrates into the soil and it attains a depth of 15 millimeters, then apparently I have a pore space of 33%, or 1/3. And water can only go into these pores. Water does not flow into the solid soil matrix. We call this the effective porosity. And of course, water reaches a depth of 50 millimeters, so the velocity of the water in this 1 hour is 15 millimeters per hour. But we can also say that 5 millimeters per hour is infiltrating into the soil. And this we call the volume flux density. So your effective groundwater velocity or your effective water velocity here is 50 millimeters per hour, and your volume flux density is 5 millimeters per hour. So this is an essential difference between effective velocity and volume flux density, both measured in, for instance, millimeter per hour, or it could be meters per day, but you see that the numbers are different. And what's the relation? Well, you can already see it. If your effective velocity is 15 and your effective porosity is 1/3, then your volume flux density is 5 millimeters per hour. Or more usually, what we do in hydrology is determine the volume flux density, and if you divide that by your effective porosity, you'll get your effective velocity. So, in summary, a rainfall intensity of 5 millimeters per hour on a 100% dry soil. Let's imagine that the water reaches a depth of 50 millimeters. That means that your pore space is 1/3 of your total soil. So you have 1/3 of pores in your soil. Your effective velocity is 50 millimeters per hour. De werkelijke snelheid, we would say in Dutch. And your volume flux density or specific discharge, je volumestroomdichtheid of specifieke afvoer, is 5 millimeters per hour. And VE equals Q divided by NE. Let's have a look at this experiment by Darcy. We have a sand-filled cylinder. So this is a cylinder. Here we have the sand, and here we have a tube, and water rises to this level in the tube, and at the right hand side water is leaving the tube again and is dripping out. So we can collect the water here and determine the amount or volume of water which is passing through the sand column. Of course, this is a screen which keeps the sand in place but lets the water flow in, and the same screen we have here. And here we see the area of your cylinder, which is also the area perpendicular to your water flow. Well, if we were to look at this screen and establish the hydraulic head here, for instance in the mid part here, this would be your elevation head, and of course this part would be your pressure head. And then elevation head plus pressure head gives you hydraulic head. Well, everywhere along this screen, whether I'm looking here or here or here or here, the hydraulic head is the same. So I have a fixed hydraulic head of H1 here. Similarly, I have a fixed hydraulic head, but a lower hydraulic head, H2 here. So water is flowing from left to right through this system. Well, let's do a thought experiment. What would happen if the difference between H1, the hydraulic head here, and the hydraulic head at this screen, if I would enlarge it? So I could rise this tube, or I could lower this end, tube. Well, intuitively, you think that the discharge or the volume flux, the volumestroom of the afvoer, would of course get bigger. So H1 minus H2, when that becomes larger, Q will become larger. What will happen when the distance x2 minus x1 diminishes? Well, of course, the porous medium which is resisting the water flow gets smaller, and it's easier for water to pass through, and your discharge would increase. What would happen if we would enlarge the area A perpendicular to your flow? Well, of course, if you enlarge this area A, you also enlarge the area of the pores within this area A, and your Q will become larger. So interestingly, this area, water is only flowing through the pores and not through the solid substances. In this instance, when we have sand grains, and water is only flowing in between sand grains. We can already establish part of Darcy's law by this, because we can see that your volume flux, your discharge, is linearly related with the difference H1 minus H2 of these two hydraulic heads. It's inversely linearly related with x2 minus x1, and it's linearly related with the area A. So here we have it again, but we can already see, okay, this is not looking very neat, because here I have a term with 2 minus a term with 1, and here it's the other way around. So let's define the difference in hydraulic head as the hydraulic head to which the water flows minus the hydraulic head from which the water flow dispatches. So through the porous water resisting medium, that's H2 minus H1. And then of course we can rewrite this part of the equation as Q being related to H2 minus H1 divided by X2 minus X1 times A, but now of course with a minus sign inserted here. In actual fact, this term, your difference in hydraulic head divided by the difference in location through which the difference in hydraulic head is attained, we call this the hydraulic gradient. And we denote that with a small I. So Q equals minus the hydraulic gradient times this area perpendicular to your water flow. In actual fact, this area A, you can look upon it as a kind of false area. Water is not flowing through the area in full, it's only flowing through the pore space in this area. Well, you see here that we need another term. And why is that? It's because if you look at this equation, this is in cubic meters per day. This is meters divided by meter, so that's dimensionless. And of course, A is in square meters. So if we have square meters here and cubic meter per day there, we're still lacking a term meter per day. And that's this term K, which is called the hydraulic conductivity. And the hydraulic conductivity has to do with the material that we have placed in between these screens. If it's sand, or if it's loam, or if it's clay, etc., this will influence your water flow also. So K, we call it the hydraulic conductivity, and it has a unit of meter per day. In actual fact, K also has to do with properties of the water. Is the water warmer or is it colder? It will mean that the density changes a little of the water, the viscosity of the water changes also, and this also influences water flow. All these variables are captured in this variable of hydraulic conductivity. So this is in actual fact already Darcy's law, but if you look in literature, you usually find it expressed as small q is minus k times your hydraulic gradient. And of course here already we recognize that this small q must be your volume flux density, because it's your volume flux divided by an area A, but this area A is containing the solid substances and the pores. But water is only flowing through the pores, and this means that this can never be a velocity, but has to be a volume flux density. If I want to know the real groundwater velocity of water flowing x1 to x2, of course I need to know the effective porosity. And here we have it. If you divide your volume flux density by your effective porosity, you will attain your effective velocity of your water flow. So we have Darcy equations in two forms here, and we have this important equation. And with this we can determine, for instance, if there was a pollution here, we can also determine the time it takes. If we know the groundwater velocity, we can determine the time it takes to reach this end of your cylinder. So to put things, to summarize things, we have volume flux or discharge Q in cubic meters per day, de volumestroom of de afvoer in kubieke meter per dag. We have volume flux density or specific discharge, small q in meters per day, de volumestroomdichtheid of specifieke afvoer, kleine q in meter per dag. And we have effective groundwater velocity, also in meter per day, but this is the real velocity of your groundwater flow. De echte, werkelijke snelheid van je waterstroming. So, if we come back to our original problem, can we determine the velocity of the groundwater flow? Yes, that's quite easy. Let's imagine that this is a sand body, a sandy aquifer. Then your K value will be in the order of 10 meters per day. And your hydraulic gradient, when this is water which can flow freely, when it's not confined in between two confining layers, but when the water table can establish itself freely, then you will find that the hydraulic gradient is approximately 1 meter per 1 kilometer. So that's 1 meter per 1,000 meter. So that's 10 to the minus 3. So if we multiply these two, we get a volume flux density of 10 to the power minus 2 meter per day, which is 1 centimeter per day. This, of course, is not the velocity. The velocity is your volume flux divided by your effective porosity. And an effective porosity of a sandy aquifer can be somewhere in the vicinity of 0.4 if it's well-sorted sand. So then we get 10 to the power minus 2 meters per day divided by 0.4, which will give you a velocity, a real velocity of 2.5 centimeters per day. Then, of course, we can also establish what the time is for water to flow from the left piezometer to the right piezometer, and with a velocity of 2.5 centimeters per day, that means that the water is flowing with a velocity of 9 meters per year, which is less than 1 kilometer in a century, or a mere stretch of 10 kilometers in 1100 years. So water is flowing very, very slowly, and this is also the reason that in our Bernoulli's law we did not need to consider kinetic energy, the energy of the water velocity. So, what did we learn? The main message: by law of nature, water flows from high to low energy, and this energy, we call it the hydraulic head. If you want to know more about hydrology, of course, you can study my book. I wish you a lot of success with your studies. Bye.